As I explained in the last class, due to thermal energy, the electrons from the valence band jump into the conduction band and they are available for current under an external influence or under the influence of some field by means of a potential applied across the semiconducting material. Okay, so in the process of giving an electron something known as a hole that forms within the semiconductor. Let us look at this diagram. So in a semiconductor lattice material, so as you know it, an atom forms covalent bond with adjacent atoms, and the electrons, it shares the electrons with the adjacent atoms and forms covalent bonds. Now when thermally generated or due to the imparting of the thermal energy, if an electron jumps out of the covalent bond, then what happens is there is a space that is formed here. So this space is free of electron. So it is known as a hole. Why is it so? So when the electron goes out of the covalent bond, so this particular atom becomes positively charged because so it has only 3 of the electrons with it. The 4th electron is out. Therefore, there is a net positive charge which is equivalent to 1 electronic charge on the atom, and there is space for an electron to come and sit and complete the covalent bond. In fact, so this is what happens when an electron loses some energy and that electron comes close to this particular atom, that electron jumps into this hole, it gets holed up and it forms the covalent bond. Because of that reason, this is known as a hole. So when the when thermal energy is imparted, the electrons are dislodged. That means a free electron is formed. Simultaneously, a hole is also formed. Now, what is the concentration? As I explained in the last class, the concentration at 300 degrees Kelvins is equal to 1.5 into 10 to the power of 10 per cc in the case of silicon. So naturally, it depends on temperature. With more temperature, with increased temperature, the number increases to some extent. And at 0 degrees Kelvins, this number is 0. Well, this is the concentration of electrons and naturally an equivalent number of holes that are formed. And what is the proportion here? So actually the concentration of silicon is 5 into 10 to the power of 22 atoms per cc of material. So when this is the concentration of silicon atoms in a material, so this is the concentration of free electrons or electron hole pair, so that is formed at 300 degrees Kelvins. That means out of how many atoms and how many of them generate a hole and pair can be clearly seen from here. It is of the order of 10 to the power of 12. Out of 10 to the power of 12 atoms, 1 atom gives a whole electron pair at 300 degrees Kelvins. Well, the concentration is low, but when you consider the bulk, the number of charged particles are moderately good in number, that is 1.5 into 10 to the power of 10, and that is good enough to give you a moderate conductivity or semiconductivity. The conductivity is in between that of metals those of metals and insulators. Now it is interesting to see how it depends on temperature. So the dependence on temperature is given by this equation. It can be mathematically analyzed and shown. So it is equivalent to some constant A naught into the absolute temperature cube into e to the power of minus the energy band gap Eg0 by Boltzmann's constant into the absolute temperature. Here, as I mentioned, Eg0 is the energy gap of the semiconductor at 0 degrees kelvins. For instance, in the case of silicon, it is 1.21 electron volt. In the case of germanium, it is less. It is of the order of 0.78 electron volts. Well, this is what happens when thermal energy is imparted to a semiconductor lattice, and let us see under the influence of field how it behaves, what kind of conductivity it gives rise to. Please note that in the earlier class I discussed about what is the conductivity of a material when the charged particle concentration is given, and the same thing can be extended now. And in the earlier class we considered only one type of charge carriers, and we got the conductivity as sigma is equal to, in fact the current density as, so n into mu into q into E. So when n is the charged particle concentration. If we have two type of charged particles, so naturally the charged particle concentration both constitutes current, and as a result the charged particle concentration becomes, if I consider n as the concentration of electrons and mu n is as the mobility of electrons, and p is the concentration of holes and mu p is the concentration of is the mobility of holes, and the charge being equal for a hole and an electron, so the current intensity would be like this in the case of a semiconductor. Please note that I have used different terms for the mobility of electrons and holes. Charge is same, concentration, although I used different terms for the concentration here, n and p. In a pure semiconductor, the number of electrons that are free electrons that are generated is equal to number of holes that are created. Therefore, n is equal to p in the case of a pure semiconductor. Okay, so this is the expression for the current intensity under the influence of a field E. Okay, so now from this, in the last class we have discussed about how to get the conductivity from this expression. So extending the same thing, which is straightforward, the conductivity of a semiconductor can now be expressed as n mu n plus p mu p into q, an electronic charge. So this is the expression for conductivity. Okay. Now here there is an underlying theory here. So we have considered, when we considered the current, we took it into consideration here, the current due to holes and the current due to electrons both. Well, it may create a question in your minds that after all the hole is created by the dislodging an electron. Do they really contribute for independent currents? since we have added the independent currents here. Well, that's what exactly happens. The both holes and electrons contribute for current. So let us look at the transport phenomenon here. So let us consider some atoms in a material. So let us say this atom has all electrons in it. Say this one is free, this particular one is free, it has contributed an electron, therefore there is a hole here, whereas these atoms are full, the covalent bond is full. Now let us say we have applied some field over here by means of an external potential difference, by creating an external potential difference. So when a field is created like this, in this fashion, electric field is created in this fashion. So the electron naturally travels towards the anode against the field, and it contributes for current. What about the hole, this hole? So this hole is not stable. So this hole is within the covalent bond. It is possible for an electron from an adjacent atom to jump into this hole, make it electrically neutral, and creating a hole here. Because the hole is in the covalent bond and other electrons are also in the covalent bonds themselves. So they are almost at the same energy level, and it is easy for an electron from an adjacent covalent bond to jump into this, and in the process effectively this hole here moves to this side. Therefore the holes also travel in this direction, in the direction of the field. As a result, both the electrons as well as the holes, although they are created by the same process, so both of them contribute for current. And the electrons being free electrons, so they can travel at a faster average speed than the holes. Therefore the mobility of the electrons and holes differ. So that is the reason why we have used the mu n here for electrons and mu p for the holes, and we have added the current components due to the electrons as well as the holes. Therefore the conductivity expression becomes this. Now in the case of silicon, let me give you some details now about silicon and germanium, which are important for our discussion further. As I said, the concentration, atoms per cc. Let me talk about some properties. As I said, this is for germanium and this is for silicon. So it is interesting to note that the density, this is per cc, grams per cc, is 5.32, and for silicon it is 2.33. The atoms per cc is equal to 4.4 into 10 to the power of 22 in the case of germanium. It is a little more, 5 into 10 to the power of 22 in the case of silicon. The energy band gap at 0 degrees Kelvins, please note that it varies slightly with temperature. At 0 degrees Kelvins, in terms of electron volts, is 0.785 in the case of germanium and 1.21 in the case of silicon. So the same thing at 300 degrees Kelvins is 0.72 and 1.1. And the free electron, whole electron pair concentration at 300 degrees Kelvins then number per cc is 2.5 into 10 to the power of 13. It is very large in the case of germanium, and it is 1.5 into 10 to the power of 10. Can you explain why the number is very large in germanium? The energy band gap is of the order of 0.785 in the case of germanium, whereas it is 1.21 in the case of silicon. Precisely because of this reason, you will find more number of whole electron pairs forming, because the conduction band is very close to the valence band, closer to the valence band than in the case of silicon. Now, the mobility of electrons, centimeter square per volt second at 300 degrees Kelvins is 3800 in the case of germanium, and it is 1300 in the case of silicon. So they differ. As we discussed earlier, it depends on the interatomic distances and various other parameters. Therefore, they differ from material to material. On the other hand, the holes, the mobility of the holes at the same temperature is, so naturally it is lower than the corresponding electron mobility. It is 1800 in germanium, and it is 500 in the case of silicon. So these are some of the important properties of the semiconductors, germanium and silicon. So far, we have been discussing about pure semiconducting materials. An interesting thing happens when you add some impurities to the semiconductors. You can really manipulate them in terms of number of carriers that are available, and thereby the resistivity and so on. And many more interesting things happen when you add them with different concentration, with different materials, and form some junction materials out of it. So let us now study about the doped semiconductors, or semiconductors with impurities, with addition of impurities. So let us consider N-type doped semiconductor. An N-type doped semiconductor forms when you add a pentavalent material to a tetravalent semiconductor. So we have several pentavalent materials available in the periodic table. As an example, antimony, phosphorus, arsenic. So these are pentavalent materials. So when you add a pentavalent material, introduce some pentavalent atoms into the lattice at a micro level. So let us see what happens. Say in the lattice we have introduced, say, a pentavalent material over here, and the neighboring atoms are tetravalent semiconducting material, say silicon. Okay. So, as usual, the silicon atoms contribute or share one electron each to the adjacent atoms and form a covalent bond. So, this pentavalent material like antimony, so it has 5 valence electrons in the outermost orbit and 4 of them take part in forming the covalent bonds with the adjacent silicon atoms, and 1 electron is left out, because in the covalent bond you have space for only 4, so 1 electron is left out. So, is it coupled? Well, it is somewhat under the influence of the nucleus, because there is a net 1 electronic positive charge. Okay. Therefore, it is under some influence, but it is not taking part in the covalent bond, therefore, it is a free electron. So, every pentavalent atom that is introduced into the semiconductor gives rise to a free electron. Is it completely free? Well, it is not completely free, because it has some influence of this +5 and -4 equal to +1 nucleus. Therefore, if you look at the energy level of this particular electron, it is not totally into the conduction band and it is not in the valence band, it is almost close to the conduction band, with the band gap between the conduction band edge and the free electron energy level is of the order of 0.05 electron volts. In the case of silicon it is 0.05 electron volts, and in the case of germanium it is 0.01 electron volts. So, this is the energy level. Well, under the influence of thermal energy, with a little bit of thermal energy imparted, this electron finds itself in the conduction band. At normal temperature, ambient temperature, you will find in fact all of these free electrons available in the conduction band, with the addition of that thermal energy. So, they are available for conduction. So, since this material, this kind of doping with pentavalent materials is donating some electrons, it is known as pentavalent doping is known as donor type of doping, and the material is known as donor material. So, it is an impure or extrinsic material. This is donor type, and it is also known as N-type semiconductor. Because normally we use N, we have been using N as a symbol for electronic concentration. Mu N is the mobility for electron and so on. Therefore, it is an N-type semiconductor, it forms an N-type semiconductor. Similarly, with a trivalent material doping, we get P-type semiconductor. So, the materials P-type or trivalent materials are boron, gallium, indium and so on. Boron, gallium, indium and so on. These are the examples for trivalent material. When you impure a semiconductor by introducing a few trivalent atoms, what happens is, so this trivalent atoms, these trivalent atoms form covalent bonds with the adjacent silicon atoms by sharing the outermost electrons with the outermost orbital electrons of the silicon atoms. And since it has only 3 electrons in the outermost orbit, it cannot form a covalent bond with one of the adjacent atoms. As a result, you have space for an electron to come, an external electron to come and sit here and form a covalent bond, or complete the covalent bond. Therefore, a p-type impurity gives rise to holes. Therefore, it forms a hole, and p-type impurity forms holes. So these holes accept external electrons. Hence, so this type of material is known as, that means the material which is doped with trivalent material is known as a p-type semiconductor. And since the holes accept electrons, this is an acceptor type material. Okay. Now, with manipulating the number of free electrons and number of holes by means of doping, we can do wonders. So before going to see what so this can do for us, before that, let me give the energy level of this p-type holes. So it is forming in the valence the covalent bonds. Therefore, the holes formed have an energy level slightly outside the valence band. So the energy gap is again of the order of 0.05 electron volts in the case of silicon, and 0.01 electron volts in the case of germanium. So where this is the energy level of the holes created by impurity, not the holes created by the thermal energy. These are the holes created by the impurity. So this is very close to the valence band. Therefore, the electrons which are present in the adjacent covalent bonds can jump into this hole, and these holes contribute for current flow. Now, when you add, yes, you have a question?
Electrons are not promoted to the conduction band.
Right.
So how the current of this?
See, that means a low energy hole itself, a low energy electron itself can jump into the hole. And when it jumps into the hole, effectively an electron is conducting, as it is as good as a hole conducting. That's what we have seen in the earlier example also. Okay? So both contribute for current. Any other question? Questions? Yeah.
Sir, why can't the free electron be shared by another tetravalent atom, sir?
Why can't a free electron be
Shared by another tetravalent atom.
free electron? You meant to say trivalent?
Yes, sir.
Trivalent material
So in n-type, sir.
in n-type?
Sir, you have a free electron, sir.
Right.
That can be shared by another tetravalent atom.
Yes. In fact, these free electrons are free to move about. Although it is under some influence of the pentavalent material, it can go to another place, and it may jump into another hole which was created because of thermal energy, and that's what may happen.
So then the octet theory will fail.
Which one?
So the octet theory for that atom will fail.
How?
If it forms 5 covalent bonds,
Right.
so then total of 10 electrons won't be stable.
That's why actually it becomes an ion. It has a net positive charge on it. Still, it can sit. When you add physically material, you can make the material uniformly distributed. Okay, and there is no other way because of the physical mixing. So it goes and sits in the lattice, and the way it happens is it forms an electron and sits into the lattice because physically you are forcing it by adding the impurity. Well, some materials which do not mix up, it's a different matter. If it mixes up, this is what happens. Yeah. Any other question?
So the holes formed, they are part of the covalent bond. So
The holes, what is a hole? There is a space for an electron to jump into it. The covalent bond is incomplete. So that's what is a hole. A space for an electron to come and jump. From which electrons? It can be, some electrons can be thermally generated free electrons can come and join. Okay, jump into it. Or it can be another electron from an adjacent covalent bond. Actually, so the material is although the lattice is an orderly structure, a particular electron can be anywhere in the material because of the uncertainty of its presence. Okay, so it is a statistical phenomenon. You can't really associate an electron to a particular atom. So they keep randomly wandering. So in the process, some holes get recombined and some new holes get formed and so on at random. Okay? Yeah, any other question?
So what is the ratio in which the impurity is added to the pure material?
You tell me. Now, at 300 degrees Kelvins, the 1.5 into 10 to the power of 10 is the whole electron pair concentration. You want to create, say, 1.5 instead of that, into 10 to the power of 10 instead of that, you want 10 to the power of 10 as the concentration. That means the conductivity will be increased by an order of 10 to the 1000 times if you want to do that. So what will be the concentration? Tell me. So naturally, see, the density is 5 into 10 to the power of 22. The thermally generated Hore electron pair is 1.5 into 10 to the power of 10. Okay, that means it is of the order of 2 into 10 to the power of 12. For every one atom in 2 into 10 to the power of 12 atoms give rise to a whole electron pair. You want 1000 more, say, electrons to occur. So you add impurity at the level of so 10 to the power of 9. So 1 atom per 10 to the power of 9 atoms. So when you do that, you will have more number of electrons forming. And the conductivity will be 1000 times. So you can design a particular material with a particular conductivity and with concentration. So that is the beauty. Okay, we can manipulate the materials. Now let us see, when you add an n-type impurity to a semiconductor, what happens to the whole concentration? So there is a law known as mass action law. So according to this mass action law, the electronic concentration into hole concentration is equal to Ni square. The free whole electron pair concentration that is formed due to thermal energy. If you are increasing N, the P will decrease geometrically so that the product is equivalent to Ni square. Why is it so? So by means of donor impurity, if you are increasing the free electron concentration, the whole concentration goes down so that the product is constant, like this. How? With more number of free electrons present in the material than the holes, what happens? Some of the free electrons combine with the holes, and as a result the whole concentration goes down. If the whole concentration and the free electron concentration before impurity addition is something like 1.5 into 10 to the power of 10, and by doping, say you rise it by 1000 times, that means 10 to the power of 13 times, what happens to the whole concentration? It drops to 1.5 into 10 to the power of 7 times. It drops by 1000 times, by a factor of 1000 times, where it rises by a factor of 1000 times. What happens to the total charge carriers? What happens to the total charge carriers now? Is it remaining constant? Earlier it was 1.5 into 10 to the power of 10 electrons and 1.5 into 10 to the power of 10 holes, and now it is 1.5 into 10 to the power of 13 electrons and 1.5 into 10 to the power of 7 holes. So this is negligibly small, and the number of charge carriers now rises to this. But the product is constant. That's what the mass action law states. If you consider an N-type semiconductor, the number of the doping concentration, let us say the doping concentration is Nd, and the number of free electrons in it is N. Free electrons due to thermal energy is N. So this is the total concentration, total electronic concentration. And P is the whole concentration. Now the mass action law says that Nd plus N into Nn into Pn is Ni square, mass action law says. So therefore Nd plus N into P is equal to Ni square. I repeat, this P is thermally generated whole concentration after doping. It goes down to 1.5 into 10 to the power of 7 in this example. It is that concentration. What about N? So for every hole there is a thermally generated electron. This N is also of the order of, is also 1.5 into 10 to the power of 7. This Nd is in this example 1.5 into 10 to the power of 13. Okay. So Nd plus N into P is equal to Ni square. What about this N when compared to Nd, when the concentration is large? It is negligibly small. Therefore the whole concentration is Ni square by Nd approximately. So Ni square is 1.5 into 10 to the power of 10 whole square by 1.5 into 10 to the power of 13, which is equal to 1.5 into 10 to the power of 7. So that's what we have shown here. Clear? So this is what the mass action law states. Well, so far we have discussed about doping of semiconductors and creating charge carriers, and these charge carriers move under the influence of electric field, contributing for some current, and thereby the material has a property, a physical property or electrical property, that is, it exhibits some conductance. Apart from the transportation of charge under a field, so there is another property of materials. So it is normally applicable for many kinds of materials and many kinds of physical bodies. We tend to diffuse from high concentration to low concentration, be it smoke which is released into the air, it diffuses from high concentration to low concentration. The same thing is applicable for a color which is introduced into a liquid. The same thing happens to the charged particles in the semiconductors. If you have a high concentration of charged particles at one place, these charged particles tend to diffuse outwards from high concentration to low concentration. And if you take a snapshot after some time, you will find that these electrons traveling in this direction, and you will find that the concentration here goes down and the extent to which the electrons are distributed increases. So this phenomenon is known as diffusion. So this is also important because in an N-type or P-type semiconductor, we have lot of a moderately good concentration of charged particles, and these charged particles can drift or move under an external field influence, and they can also diffuse when there is no field. They can diffuse from high concentration to low concentration. Okay. Now this can be mathematically expressed. The phenomenon of diffusion can be mathematically expressed, and the current that is contributed due to this movement from high concentration to low concentration is proportional to the concentration gradient. Say you have only a one-dimensional space, a two-dimensional space, but there is a uniform concentration along the y direction with concentration gradient, with some concentration gradient in the x direction spatially. Therefore, so the charged particles tend to move along the positive x direction from high concentration to low concentration. If the concentration as a function of x is nx and its gradient is naturally dnx by dx, and the current is proportional to this with a negative sign, because from a high concentration to low concentration area, these charged particles diffuse from a high concentration to low concentration area. Therefore, when dnx by dx is negative, the current is positive in that direction. Hence, the current contributed by, for example, the holes, the diffusion of holes from high concentration to low concentration can be expressed as, so minus q, so dp into the, so dp by dx, where p is the concentration as a function of x of the holes, concentration of the holes as a function of x, and dp by dx is the gradient. So naturally the number is proportional, number that is getting diffused is proportional to the gradient, and the charge that is getting diffused is q into that, and the proportionality constant is dp. So this is known as diffusion constant. This is measured in terms of meter square per second. So in a semiconductor, when you have a concentration of charged particles, you can expect the charged particle to diffuse, and if there is an external field, you can expect the charged particles to drift under the influence of the field. Right? This is what happens in a p-n junction. In a p-n junction with p-type material and n-type material, say you have a p-type bar and an n-type semiconductor bar, you bring them together and form a very good, very clean junction. The concentration, the high concentration of holes from the p side get diffused to the low concentration on the n side, and similarly the electrons from the n side get diffused into the p-type material. So this diffusion takes place in a junction. Okay, so we shall just look at this diagram, p-n junction. So we have p-type material and n-type material. P-type material means we have some holes throughout the material, and we have some electrons throughout the material, high concentration of electrons throughout the material as the majority carriers. Are there holes also? Yes, some minority carriers which are really minority, like in the example we considered, where this is of the order of 10 to the power of 13, this is of the order of 10 to the power of 7. So these are minority carriers, holes are minority carriers in an n-type material, and the electrons are majority carriers. Similarly for the p-type material, with the holes being the majority carriers and the electrons being the minority carriers. Now, because of high concentration, these holes diffuse into the n-type from p side, and the electrons diffuse into the p-type. So as a result, what happens is, after a small amount of time, so this side will be free of these free electrons. There will be no free electron left out almost. So there would be no free hole left out on this direction because of this diffusion. And as a result, because of losing an electron, you have positively charged ions left out. Positively charged pentavalent ions left out, because that free electron has gone, therefore that net positive unit charge, which is immobile, because these are nuclei. Okay, so with net positive charge equal to 1 electronic charge, and here you have net negative charge left out. So this is known as space charge, and this region is known as a depletion region, because this region is depleted of mobile charges. It has charge but immobile charge. These are depleted of mobile charges, therefore it is known as depletion region. So we shall continue this discussion in the next class.